Hi all, welcome back to Environmental Science Lectures, and we're going to finish talking a little bit about communities. We're trying to get this concept of what a community is. Okay, we talked about that before, all the species that occupy the same region. But then how do we define a community? Do we define a community as one kind of superorganism? Like it works together and we must maintain all the parts? Or do we define a community by the individuals that are in the community? And really that brings me to kind of two views that exist on how communities form, what's the functionality of communities, etc. And one view is from Gleason, H.A. Gleason. It's an old view, and that view is individualistic concept. Okay, and that is that a community is nothing more than just the species that occupy that area at a given time, and that if you take a species away, a species will come and fill that niche, which we'll get to in a second about kind of niche or niche hypothesis and what that means. But if you remove an individual, another individual will come in and fill that gap. That's the kind of the individualistic concept, and in many cases this may be true. The other concept is what Clements put forth, and it's called the holistic concept, and that is viewed as the community is a superorganism. And if you change that community in any way, if you remove an individual, if you remove a unit, you change the superorganism. He's not saying, Clement at the time was not saying that the superorganism goes away, but the superorganism is changed. Okay? And it's not the same superorganism. So two kind of concepts, and really it comes about based on what we call the niche concept, or the concept of a niche. Okay, so depending on how you want to say it, doesn't really matter to me. I call it a niche. The term really started from people who used to build fireplaces. So old fireplaces, when they're built out of brick or rock, often the person who built it would leave kind of in a certain region, maybe up high away from the reach of little children. They would leave a brick out or leave a rock out, and it would create this space, which at the time they called a niche. Okay, this space, and that's where you would put things like matches and maybe some type of like material to start a fire with. Okay, and that would go in that little teeny compartment, that little teeny area that that has its own place, and that's where the concept came from. That's where biologists stole the word from, and really what it means is this specialized area that is an organism is suited for, and that's both abiotic. The A part means non, so biotic means life, so abiotic means non-living. So this is things like temperature, precipitation, pH, all the things that we're often interested in environmental science, collecting on the environment and how that changes. Those are abiotic characteristics. And then biotic characteristics are the living characteristics, so the living organisms. That could be the plants, the bacteria, the fungi, the other animals, okay, whatever it is that we're interested in. Normally we're talking about this from an animal perspective, but we could be talking about it from a plant or a fungi perspective or a protozoan perspective. It doesn't really matter. Niche is both non-living and living environment in just a small given region. And what's been put forth for a long time is that we know that two species, or no two species, can occupy the exact same niche. Okay? So when you have two species that occupy the same niche in an environment, you get competition. And what happens with that competition is, if the competition is severe, those organisms will be displaced. Okay? One species will be displaced. There's not enough resources in the environment to satisfy both species, so one has to be moved. It has to occupy a different niche. And that's really where that competition comes into play. Sometimes this is between different species, which we call inter-specific competition. Okay, the inter part means different. Okay, intra means same or within. So inter is between species. Intra means within the same species, and it holds true. There's always going to be competition. Now, intraspecific competition within the same species is competition that normally it's documented, and it will determine population size. Okay, so often intraspecific competition is going to set the carrying capacity of the environment. Okay, but interspecific competition between species, often you get this competition that separates species, so they don't occupy the same niche any longer. So, for example, if we look at, say, barnacles, and you can get these two species of barnacles, semi-balanalis, okay, so this larger barnacle, and thamalis, this smaller barnacle here, right? They have what we call a fundamental niche, which means fundamental niche means that this is a region that they could be found. Best case scenario. So can they establish both populations in shallow regions and populations in deeper regions? Well, thamalis can. Okay, but the semi-balanalis, it outcompetes it in deeper regions. Maybe it's better at filter feeding. Maybe it just takes up more space. Maybe it excretes some kind of chemical that doesn't allow these individuals to get established. So it moves them. So now these two species do not occupy the same niche. This is a shallow niche, a different environment. This is a deeper niche. Okay? If we removed semi-banalis, then thamalis would increase its presence, and it would move deeper, okay, and it would occupy its fundamental niche, or closer to its fundamental niche. Okay? So this is the difference between what we call a fundamental niche and a realized niche. The realized niche is where you actually find them. The fundamental niche is how, or the range at which they can occupy. Okay, so fundamental niche is the entire niche that an organism can theoretically occupy. So this is based on temperature, precipitation, pH, water flow, whatever environment we're talking about. Okay? Maybe it's habitat to build nests, all these kind of things. Okay, that's fundamental niche. Okay, along with biotic species. So if there's no competition, where would you find them? Okay, and then your realized niche is when there's competition around, when there's other species that have overlapping fundamental niches. Okay, then where do you actually find them? Okay, and that's the competitive exclusion. Okay, so that's what we typically call niche exclusion or competitive exclusion between species. That no two species can occupy the same niche at the same time. Okay, so that gets at Gauss's demonstration of the principle of competitive exclusion. We just talked about it. Okay, so if two species are competing for a resource, one species will be eliminated from that area. Okay? No two species can occupy the same niche. Okay? And we can show examples of this in laboratories, in marine environments, terrestrial environments. Everywhere that we've kind of looked, we can find examples of this. A classic example was done in a laboratory when we were looking at paramecium. Paramecium, you guys saw paramecium when you were looking at water samples under the microscope. You can see paramecium, little protozoan organisms. Well, there are different species, okay, of paramecium, and we can put them in, different environments, and you can look at their logistic growth curves. Okay, so you put them in the environment and you measure how fast they grow and what their population reaches. And just like we talked about before, okay, they'll have exponential growth rates and then they'll reach a carrying capacity. Okay, so in this case, the carrying capacity of Aurelia is somewhere probably around 180, okay, measured by volume. Okay, Catadetum, okay, same deal, about 180. So both these organisms feeding on the same things. Okay, both these organisms occupy kind of the same carrying capacity. Bersaer, okay, their carrying capacity is a little bit lower. Maybe they need more resources. So they're about 120 carrying capacity, etc. Now, in an experiment which was done a long time ago in the 60s, okay, if you put these together, let's see what happens. Okay, so Catadetum and Aurelia, who had overlapping carrying capacities at about 180 or so. So when you put them together, one gets outcompeted. Okay, Catadetum loses; its population declines almost to nothing. Okay, now there may be a few individuals that are holding on, which is what's causing the carrying capacity of Aurelia to drop. Okay, so it's no longer at that optimal 80. It is, due to competition, it is lowered. Okay, but then again, they're out competing this other species. If you put the two that had lower carrying capacities, okay, they seem to be able to share the environment. Okay, even though their populations are much smaller, their populations don't reach their original carrying capacity. Neither species drops to zero. Okay, Bruceria is lower, okay, but Catadetum is also lower, and so, but the two species seem to be able to share resources. Okay, this is normally what we call resource partitioning. So maybe they share resources from the perspective of one occupies a deeper part of the water column and the other one occupies a shallow part of the water column. In this case, the competition causes one to basically be non-existent. Okay. In general, it's in the best case scenario for a species to avoid competition whenever possible. Competition, in the case of survival, competition is expenditure of energy. And extreme competition typically means survivability decreases. Okay, so when you have overlapping niches, you have really two kind of outcomes. You have competitive exclusion, which we saw in that first example. Basically, winner takes all. Okay, you outcompete them and they have to find a new habitat, a new place to exist. Or you have resource partitioning, which divides up the resources and creates two new niches. Okay, now they're not equally divided. Okay, it's not like one organism says to the other organism, hey, we're going to divide this down the middle, and share the resource. That's normally not what happens. But the competition is so fierce that one organism moves, and the other organism, because they're so close from a competitive perspective, the other organism's happy with what they have and is excluded into a single niche, and then the other organism is excluded into a new niche. Often in natural situations, competition is kind of rare. At least direct competition, constant competition is rare, because again, like I said, extreme competition is energy expenditure that most organisms can't afford. Okay, so energy in many situations is limited, and you can't just constantly expend energy to compete against a neighboring species. So often what will happen is one species will move. You'll have resource partitioning, or one species will just move altogether and try to find a new habitat. If it continues for a very long time, normally what happens is one species drives the other species to extinction, or the other species, through natural selection, develops new characteristics that give them an advantage in a new environment or in the current environment. Okay? And so sometimes this will happen with species that are parasitic, and you'll get things that we call like an evolutionary arms race. One species changes, the other species changes, and it goes back and forth like that. But through natural selection, you're having organisms change to compete with each other, and that can happen also. Okay? So let's look at an example of resource partitioning. So we might have a bunch of different lizards. These are anole lizards or anolis lizards, and they might occupy different areas of a tree. Okay, so you might have one that occupies, say, the base of the tree or the vegetation along the bottom of the tree. You might have one that occupies the trunk of the tree, one that occupies the canopy of the tree, and then one that maybe was excluded from that species of tree and had to move to a different species of tree. So we've seen this occur especially on islands. When anole species evolve in islands, you'll see within one tree you might have 3-4 species of anoles, and they look different. They're genetically very similar from the perspective of they might be the same genera, the same genus, but they're different species. And you can tell that they evolved to occupy different regions of the same type of vegetation. Just an example. Okay. Okay, often when we have resource partitioning, it's the result of similar species occupying similar geographic areas. This will happen often when we introduce species. Exotic species will come into an environment, and the environment they once existed in, their native environment, they're trying to occupy that same niche in a new environment. And there's already a species there, so they will have competition. Sometimes they lose that competition, and that exotic species, that non-native species, doesn't ever get established. Sometimes they're better at competition and they remove the native species. And so normally when we look at examples of exotic species coming in, we see the bad. We see what happens when you introduce a species that gets established and it outcompetes the native species. We rarely get to see when you introduce a species and it doesn't work, okay? Because we don't want to really introduce species. We used to move species around all the time and introduce them all over the place, and many times we'd introduce them and they just wouldn't work. They're not suited for that environment, or the organisms that were already in that environment are better suited for that environment and outcompete them. Okay? But when we have species that are very similar, occupying the same geographic area, we can have what we call sympatric speciation. Okay? That's where species occupy similar habitats, okay? But they have greater differences in morphology. So they evolve differences, okay, for dealing with different pieces of that environment. Okay? And so we call that sympatric speciation. And then we have another example, which we call allopatric speciation. And that's when they occupy different habitats but have similar characteristics. Okay? And that allopatric speciation is problematic when you put or introduce an allopatric species with another species that has very similar conditions, behaviors, morphology in a different environment. Right? And we'll talk more about some examples of this. Right? And often we're talking about it from sympatric speciation, so how species develop. We call it sympatric speciation, where they occupy the same habitat but tend to have different morphologies. Okay? Or allopatric speciation, where their morphologies are similar but they occupy different habitats. Okay? We talk about this from kind of evolutionary terms, how species evolve and how they change. Now, humans are really good from an environmental science perspective. We're really good at moving species around or changing habitats, or both. And so we can alter both sympatric speciation and allopatric speciation. And part of that is, the differences between species are often called character displacement, and they're displaced or they occur based on the natural selection of a given habitat. This becomes a problem when your habitat is changing. Maybe a character that was once displaced in the organism for maybe millions of years, the organism has been down a trajectory to have a certain skin color, okay? And then the environment changes due to human alteration, and now that skin color is a disadvantage, or that coat color is a disadvantage, or that head shape is a disadvantage, or that leaf structure is a disadvantage, okay? And so that organism, which was down a certain evolutionary trajectory, its character has been displaced that would give it an advantage in the current environment. Okay? All right. We'll come back and talk about coevolution and symbiosis next time.